So in section 6.5, we're going to talk about the central limit theorem. And this section connects doing sampling distributions and the normal distribution. So there's two things we know. We know that if we have a distribution, we know its mean and its standard deviation, okay? And then we're also doing a sampling. We're going to collect all possible samples of some size n, okay? So n is our sample size. Now, the distribution of the means, if we take these samples and then we find the average of each sample, and now those are our data points. And the distribution of all these means will take the shape of a normal distribution. If the population is already normal, if it's bell-shaped, or if the sample size is big enough. So even if the original distribution wasn't normal, if we take big enough samples and we look at the averages, those averages become a normal bell-shaped curve. Okay, if the original population already is normal, then the sample size can be anything. So it can be 1 or larger. 1 would really not be a sample. You would just have the original distribution. If it's not normal, then our sample size has to be at least 30. Now, here's kind of the big picture idea of the central limit theorem. The distribution of means, so if we look at all the means of the samples, it gets narrower and steeper. So it's still, if our population looks like this, a nice bell-shaped curve, okay, then our sample means it's going to peak at the same spot, but it's going to be much more compact. And we can actually easily calculate the mean and the standard deviation of this new distribution we're looking at, of the means. So the mean is going to be the exact same as the mean of the original distribution. So exactly the same. We don't have to do anything. The thing that changes, because we said it peaked at the same spot, the thing that changes is the standard deviation. And the standard deviation, we take the standard deviation of the original distribution and we divide it by the square root of n. And that's our new standard deviation that we call sigma x bar. Okay, so when we're taking samples of some size, we'll have to use mu x bar, which is the same as mu, and sigma x bar. If we're just looking at one thing from our distribution, we'll do it like we have in the older problems. Okay, so this first problem says women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. So it says sketch this distribution showing the mean and the standard deviation. So the original distribution, if we're just looking at each, women individually, we've got a normal distribution. The mean is at 63.6. And, we can just say the standard deviation is 2.5. So, we could kind of go a couple standard deviations on each side, but this will be sufficient. Now, part B says, given all samples of size 16, so we're looking, our n is 16. So we're taking 16 women at a time and finding the average height of those 16 women. Now, this distribution, like we said, it's going to peak at the same place. The mean of this distribution, is still going to be 63.6. But now the standard deviation is going to be smaller. It's going to be sigma, the original, over the square root of our sample size, so over the square root of 16. If we take 2.5 divided by the square root of 16, we get 0.625. So we see we have a much smaller standard deviation. So it's still going to peak. This isn't a great normal distribution picture, but it's still going to peak at 63.6, but it's going to be narrower because the standard deviation is only 0.625. So part C says, if one woman is randomly selected, what's the probability her height is between 60 and 65 inches? Now, since we're just talking about one woman, not a group of them, we're going to use the original distribution. Okay, and we'll use everything we've learned in previous sections. We can use our calculator. We'll find the z-scores, then we'll use our calculator. So we'll find the z-score of 60, which would be 60 minus 63.6 over 2.5. and there that gives you negative 1.44. And we'll find the z-score of 65, which would be 65 minus 63.6 over 2.5. Notice we're using the original mean and the original standard deviation. This gives us 0.56. So now to find the area between those two z-scores, remember, we do normal CDF, which is under, remember you hit second vars under the distribution. We do negative 1.44, comma, 0.56, and when you put that into your calculator, you get 0.6373. So that means the probability that if one woman is randomly selected, the probability that her height is between 60 and 65 inches, this would be about 63.73%. Okay, now how this changes, the next part says if 16 women are randomly selected, what's the probability that their mean height is between 60 and 65 inches? So if we pick 16 women and we take the average height, what's the probability that their height's between 60 and 65 inches? And we should expect that this is a higher probability because if we're taking an average, if we happen to have a really tall woman or a really short woman, they're averaging out. Okay, so now remember here we have to use the mean, still 63.6, but when we find the z-score, the standard deviation, we have to use a sigma x bar, which is 0.625. So we're going to find the z-score of 60 using these, so 60 minus 63.6 over 0.625, which if you put that in your calculator, that gives you negative 5.76. And if we do the z-score of 65, we would have 65 minus 63.6 over 0.625, which would give us 2.24. So again, now that we have these z-scores and we use the different standard deviation, we go back and we use the normal CDF, just like we did above, and we go from negative 5.76 to 2.24. And we see our probability here is 0.9875. So if we take 16 women and we take their average, the probability that their height is between 60, their mean height, and 65 is 98.75%. Okay, so kind of the moral of the story here is if you're taking a sample of some size, like here 16 women, it wasn't just one woman, then that's when you're going to use sigma x bar. Okay, we've got one more application here. So it says, a ski gondola carries skiers to the top of the mountain. Its maximum capacity for 12 people is 2,004 pounds. Now, if we take 2,004 pounds and divide that by the 12 people, that gives us each person on average can weigh 167 pounds. Because men tend to weigh more than women, a worst case scenario would be 12 passengers who are all men. And it tells us that men have weights that are normally distributed with a mean of 172, so that means mu equals 172, and a standard deviation of 29. Now, this says, since we're looking at 12 men on a gondola, we want to sketch the distribution of means of all samples of size 12. So here we'd have mu of x bar, which is still the same as mu, 172. But our sigma x bar, we would take sigma 29 divided by the square root of 12. So that would give us 8.37. Okay, so we have a normal distribution where the mean is at 172 and our standard deviation is 8.37. So now it says find the probability that 12 randomly selected men will have a total weight of more than 2,004 pounds. That is, find the probability that the mean weight of these 12 men will be greater than 167. Okay, so we want the probability that the average is greater than 167 pounds. So first we're going to find the z-score of 167, which will be 167 minus 172 over our sigma x bar, so 8.37. This gives us negative 0.597. So now since we want everything greater than that, we're going to go from that z-score up to 1,000. So we're going to do normal CDF of negative 0.597 up to 1,000. If you put that in your calculator, this is going to give us 0.7247. So the probability that their mean weight is greater than 167 pounds is about 72.47%. So what this is saying is, if you have 12 men get on the gondola, we've got a 72% chance that gondola is overweight.